Okay, so in the last lecture, we did the derivation of pressure and we got a variety of formulas. So we got P equals to 1/3 of density of gas into VRMS whole square, right? So this was the first equation that we got. And from here we got VRMS equals to 3P by rho. And this is the molecular velocity RMS value. So if you think of each and every molecule, they have different speed, and this is the RMS value of the molecules taken together. Okay, also we have the relation PV equals to nRT, and this we can write as PM equals to rho RT, or P equals to CKT. So these are all three equations which you can convert. C is the molecular concentration. Okay, and once you substitute the value, now the VRMS turns out to be how much? 3RT by
M.
M. Yeah, so this is the 3RT by M, and this is the RMS velocity as defined for molecules. RMS value also defines a process called a process of effusion. So what is effusion?
Diffusion through small holes.
How small?
Very small.
How very small? So if the diameter or opening aperture size is you can say less than the mean free path. So in a way, it is like at one go only one molecule can come out of it. It's so small. So if at one go only one molecule will come, so it will definitely come with what speed? RMS, the molecular speed, right? The average molecular speed you can talk about.
Yeah.
In effusion, the orifice is smaller than the mean free path or comparable with the mean free path. So it is like the stream of particle will not come. Okay. So what will come out is only the particle one by one. It's such a small gate that only one person can pass at one time. So even though all will come outside, but they will come one after the other. So there is a effusion. But if the size is large enough, then a large number of molecules can come together. And when it happens, we call it diffusion, right? So diffusion is slightly different. What is diffusion? It is again an orifice, but the D is much bigger than lambda, which means it is a small orifice, but the size is big enough to allow a large number of molecule to come together as a stream or as a jet of molecular particles. So this is a small difference between the effusion and diffusion. Just for theoretical knowledge, you shouldn't be knowing this. I think in detail you must be studying in chemistry, the Graham's law of diffusion, right?
Yes, sir.
Yes, sir.
And you can clearly see that effusion we can understand because the formula is 3 RT by M. So for a given temperature, the RMS speed is what? It is a square root of molecular speed, right? Molecular mass.
Yes, sir.
And because it is inversely proportional to the molecular mass, which means more the mass,
Less the speed.
less the speed. So in a mixture of gas, which gas will come first in a process of effusion?
Having less mass.
Having less mass will have more, you can say RMS, and
RMS speed.
it is a generally a tendency for the lighter particle to come out of the orifice. It's like a relative competition, and the winner will be the one which having lesser mass. Okay. Okay, so just theoretically you should be knowing this, and VRMS will decide the process of effusion And therefore, if you have a mixture of gas, you should be knowing theoretically that a lighter mass particle will come first, relatively. Now, C is the molecular concentration, which means it is the number of molecules per unit volume. So you can think this way, N by V. See, it is not the molar concentration, because in chemistry, what you generally study is N by V, right? The moles per volume, right? And
Yes.
the molar concentration you represent in a bracket, the square bracket symbol, right? When you study the chemical kinetics or chemical equilibria, so you use the square bracket symbol that represents the molar concentration, right?
Yes, sir.
Anyway, so there everything is defined in terms of 1 mole of something. So it is convenient when you discuss thing in mole, then it is convenient to write. The other formula that one should be aware of, I mean, just as a recap, so VRMS, you can write, of course, for the molar mass. You can also write in terms of Boltzmann constant, 3 kT by small m. Now, the moment I'm writing like this, 3 kT by small m, the K represents what? Boltzmann constant. And what is the value of Boltzmann constant, if you remember?
So 1.38 into 10
10
raised to
minus
minus
33.
3
And what is the unit of this?
joule per Kelvin.
Joule per
Kelvin.
Kelvin. Very good. So once you multiply K with temperature, what you get is joule, right?
Energy.
The energy dimensionally. So when you're solving the question of dimensional analysis in JEE-Mains or advanced, the moment you see somewhere the KT written, think as a joule. So that will make the calculation easy. Okay. So this is energy, and if I write something like okay, these things you should know that half or not half is not available. So dimensionally, certain things you should know that whenever you see these two together, it's energy density. When you see B square by 2 mu naught, energy density. So we'll anyway come to those things also. But just for the question based on dimensional analysis in JEE-Mains, these three terms are often used for making the question complex in appearance. So of course you can put half here. So anyway. So we're talking about the dimensional relation, not the actual relation. So KT absolutely not E square, B square mu naught. Also, you can see that F equals to, if you write the coulombs, let's say KQ square by R square. Okay. So F R square is how much? Q square by 4 pi absolute naught. So why I'm writing this? Because generally Q square by absolute naught will have the same dimension as FR square. So from the past experience, I have come to know that, okay, if someone is knowing this much, then dimensional question you can solve really fast, because you need to know how to convert things as quick as possible. Okay. So you have to keep in mind that everything we need to write this. And once you get something in joule, it becomes FR. Once you get something in density, it is FR by R cube. You can think this way. So it's easy to convert things in force, and then easy to write things. The dimension calculation doesn't need, you need to substitute each and every bit of it. It requires your knowledge about the overall relation, which you can reduce as fast as possible. So some tricks to solve dimensional equation. Okay. Okay. Now, because the VRMS you got as 3 kT by m. So you can see the kinetic energy of each molecule is how much? So mv square becomes how much? 3 kT, so half mv square. This is called the kinetic energy of each molecule you can think of. So it turns out to be 3 by 2 kT. Okay. So this is what we studied in the last lecture. I hope you remember right all this thing. So now comes the next part, which is concept of equipartition of energy and degrees of freedom. So we'll try to understand the degrees of freedom first, then we'll go to the equipartition concept. To understand the degrees of freedom, we need to go back to something very simple. Let's say if I give you the example of if a person is walking a tightrope. So if a person is walking a tightrope, then how many degrees of freedom the person is having while walking the tightrope? So simply means
One.
like
1 degree of freedom.
yeah, it is only one degree freedom. It's like the rope is the only path you can traverse, right?
Yes, sir.
Now, if you are on the ground, then how many degrees of freedom you have?
2.
So the answer is 2, because in any plane, how many variables you need to explain the motion? So we need just 2 variables, x and y, right? Sufficient. So in any planar motion can be described with the help of only 2 components, which is vx and vy, right? So you can choose any direction, but every direction can be explained in terms of vx and vy, correct? So on a tightrope, we have only 1 degree of freedom. And now this degree of freedom which you are talking about is called the translational degree of freedom. But in a plane, the degree of freedom becomes twice. I mean, it is 2. But in a 3-dimensional space, how many degrees of freedom the particle can have?
3.
So now a particle can move in any random direction, but to describe its motion, now listen this carefully. The particle is free to move in any direction. But to describe its motion, what is the minimum number of variables we need? So we need Vx, Vy, and Vz, right? So can we say that 3 components are sufficient to explain the motion of a particle in 3 dimensions? Yes or no?
Yes, sir.
So from this discussion, what we can say, what exactly is degrees of freedom? So what is degree of freedom? What should be the definition? So there are many definitions. One is a definition based on the motion, another is the based on energy. When you study the degree of freedom for the first time, in any higher studies, they start with the motion. Okay. Okay. So degrees of freedom, it is the minimum. It is the minimum number of parameters required to explain the motion of any system. So degree of freedom is the minimum number of parameters required to explain the motion of any system. So if you have a system may be a molecule also, system may be a real life, a three-dimensional object also, system may be a rigid body also. So whatever you have seen, basically this concept was introduced in the chapter of rotational dynamics to explain the world, because degrees of freedom is the very generalized process in which we describe the motion of system. And we believe that if we have the number of equation which is equivalent of the number of degrees of freedom, then the motion can be completely analyzed, described mathematically. So that's the whole idea. So it is the minimum number of parameters required to explain the required to completely, I would say, completely explain the motion of any system. So it is that you want to describe someone's motion, and then you're looking for how many variables you need to explain the motion. Now, when it comes to motion, so in kinematics, what you study is called the linear motion, curvilinear motion or rectilinear motion, right? So how many types of motion you know? So let me give you the example of H2 molecule. If you want to imagine H2 molecule as some rigid body system, then it is like 2H atoms, and they are at some separation, and therefore every molecule can be modeled into a spring mass system, and it is such that the attraction and the repulsion is balanced perfectly. So why we are saying spring block system? Because in a perfectly balanced system, in a stable equilibrium, if you try to bring it closer, it will repel, and if you try to bring it far apart, it will attract and pull it back. Now, this both events can be described with the help of spring configuration, because in spring, if you stretch the molecule, if you try to stretch the molecule, what will happen? The spring force will try to pull it back, right?
Yes.
And if you try to compress it, again, the spring system will try to push you back. Okay. So now the spring is like a something, you can say a model. It's not a, I mean, exactly spring. I mean, there's nothing like a spring in between. But this is how we can model any, you can say molecule or any configuration of atoms. So this configuration or this assumption is very powerful, because the spring will have a very different behavior. It's a very unpredictable behavior of the spring. So it may be a spring which you use in your, this normal pen, which you press, and there's a spring action. This spring may be as tough as the spring of the you can say the wheel of the railway coaches. So if you have seen the railway coaches, below it there is a wheel and there is a spring. You must have seen the spring is very thick, right? And this is so thick that the weight of the train, which is in tons, that weight is able to push it slightly. So imagine if that spring is connected between the lighter object, will it move at all?
No,
The
sir.
spring will move. So the answer is no. The spring is as good as a rigid body. So what happens? This behavior of the spring varies over temperature. So you can say that as you increase the temperature, the spring softens. Okay, it becomes soft in nature, and the vibration starts happening in a molecule. So we say that there is something called vibrational motion. And now this vibrational motion is generally a function of temperature. And at a different temperature, the molecule can exhibit some complex motion. Okay. So we have three types of motion that we generally study in this concept of degree of freedom. A molecule is not a single entity. So if I give you a just only single atom, for a single atom, can we think of vibration?
Yes, sir.
Can we think of single atom as a, I mean, like, is it possible to for single atom to vibrate?
Yes, sir.
Okay, is it possible? How
Sir,
single atom can vibrate?
sir, why can't
Vibration
it
is-
vibrate?
No. Vibration is only possible when we have two or more than two atoms attracted to each other and creating a stable configuration. Then you disturb the configuration, then they oscillate. A single atom is not bound to anything, right?
Oh, yes, sir.
And if an atom is not bound to anything, then how and why it will vibrate? Tell me.
So it won't vibrate.
So there is no
Okay.
question of vibration. The second thing is it possible for a single atom to have rotation?
No.
Why not? It can have rotation. So we have moment of inertia.
Oh, yeah. Yes, sir, it can.
So what is the moment of inertia of a sphere of radius r?
2 by mr.
This is the moment of inertia of a sphere. So a single atom can have rotation, yes or no?
Yes, sir.
Now this is something contradictory here. In KTG, what is the dimension of atom we assume? We assume R to be very small, isn't it? So the assumption, because of the assumption of this KTG, R is tending to 0. So basically, this entire atom will shrink close to the axis itself, isn't it? And if something is almost overlapping with the axis, what is the moment of inertia of this particle?
0.
Which means, though it may rotate, we cannot deny it, but such rotation will be effortless. Understood? Are you getting my point? What I'm saying?
Yes, sir.
So let's say, I mean, you can think as a small kid will be very happy if you give just one chocolate. Okay, you're not supposed to buy the entire this Cadbury celebration or some stock of chocolate. You just buy one small chocolate and they will be happy because they are like not so much greedy. The opposite case is also possible, but generally, if it is very small kid, they are very happy with one chocolate, isn't it? So giving one chocolate is not a very costly affair. So we can think such process as energy-less process because there is no good deal of energy exchange, isn't it? So imagine if you are giving someone a bouquet of chocolate and someone else you are giving just one single toffee, okay, 50 paise, some toffee. Then compared to that bouquet of chocolate and this one toffee, what is the relation? Can we ignore this energy relation associated with the one toffee? Tell me yes or no.
Yes, sir.
So why I'm saying this? Because to set something into rotation about an axis, which offers a roughly 0 moment of inertia, will take almost 0 energy. Yes or no?
Yes, sir.
Do you all realize this? What I'm saying? See what is happening. We are trying to understand that, as I said, the energy which we talk about is the kinetic energy of molecule, right? I said that the internal energy is nothing but the kinetic energy of molecule.
Kinetic energy.
What you don't realize that when I described the kinetic energy in the last lecture, Which energy I described? Do you realize this? Was it rotational, vibrational, or translational?
Translational.
I only described the translation because I was using Vx, Vy, Vz, right?
Yeah.
Did I use omega x, omega y, omega z?
No.
No. So whatever I have explained so far in the last lecture, it was only meant for the translation. But kinetic energy cannot have only one form. It can have basically three forms. So what you need to understand that if you have kinetic energy, then the same energy can be stored in three possible ways. You can store the kinetic energy as translational. Now, translational energy is as good as the energy of center mass. So energy carried by center mass kinetic energy, I can add this is K of Cm of system. Now again, I'm saying system here is molecules. So translational means you are only looking at the motion of center mass. You are not looking at the individual parts of the system. And in case of multi, you can say atom system or polyatomic system, you can say. So for polyatomic system, we cannot only rely on the fact that it will have only one form of energy, that is translation. No, a polyatomic system can exhibit other form of also kinetic energy, which is like rotational and vibrational. Understood?
Yes, sir.
So when you switch on the fan, which energy you see? If you think fan is a system, so when you switch on a fan, what do you see? Do you see the center mass moving on the fan?
So we see only rotational kinetic energy.
Correct. So what you see in general is the only rotational energy because center mass is still at rest. So which energy it is missing?
So translational.
Yeah. So the fan will not have the translational energy. Still, it will have the kinetic energy. Because kinetic energy, I mean, is not supposed to be only in one form. It could be in a form of rotation, it could be in form of translation, and sometimes it could be in the form of vibration. Understood?
Yes, sir.
So now, I mean, if you have seen, let's say, a spring block system, if I compress two block connected with a spring and release on a surface, what will happen? What will move, what will not move? You compress and release simply.
So the
Center mass
center
will
of
move.
mass will not move.
Correct. Why?
So because the net force that is applied on the system is zero.
Correct. So center mass was at rest. And even
Yes.
though you release the system, because there is no external force to accelerate the system, center mass will still remain at rest. And because
Yes.
the block will oscillate, so the kind of energy that you can link for a system, of course, you can say that energy is translational of individual block, but when you think system as a whole, then you have to say that as a vibrational kinetic energy. So in a system where center mass is well defined, if center mass is at rest, then it can still have the kinetic energy, but in other form. And the other form may be translational or rotational or vibrational. Understood what I'm saying?
Yes.
Now imagine the third scenario. You take two blocks connected with a spring, you compress it. Okay. And while compressing, what you do? You throw it as a whole. And while you throw, the spring is released. I mean, it is no longer compressed. And you throw with some twist also. So it will perform what kind of motion? So if you have a two block system, which you have compressed and you have given a twist and forward velocity, what will happen?
So
So
it will have all three types of.
Yeah. So center mass will move the parabolic path. And across this parabolic path, the molecule will vibrate as well as rotate. Understood? So vibration so the molecule as a whole will translate because center mass is moving, will oscillate because the spring is compressed, and the orientation of the two ball or the two masses will shift. So we can say there is a rotation also involved. In such motion, it is really complex motion. The system, because this is our two mass system, the system as a whole is performing all the three types of motion: translation, rotational, and vibration. So the energy it will carry will be in three formats. So the total kinetic energy of such system in which we have a rotation, which we have in which we have vibration also, you have to add all the energy form. Understood?
Yes, sir.
So why we are studying degree of freedom? Because this all motion requires some variables to be explained, to be defined, to be put mathematically. So like if you want to describe the translational energy, you need translation motion variables. You need Vx, Vy, Vz. So if you want to describe the rotational kinetic energy, what you need? The rotational variable like omega x, omega y, omega z, Ix, Iy, Iz. And if you have the vibrational, now vibrational and rotational both are only possible for the polyatomic system. But translational is performed or is meant for all types of system, whether it's monatomic or polyatomic, doesn't matter. So we have three types of energy, and to describe all the energy, we need all such variables also. What is really interesting to understand here that vibrational involves minimum two particles together. So a single particle cannot have vibration. Similarly, rotation cannot be possible for one particle because the particle that we consider is small enough not to, suffer any rotation, or you can say the rotational motion is kind of insignificant motion because you won't be able to watch it. It's a very small value. And therefore, the energy associated with a single atom, the rotational energy, you can say linked with it, will be negligible compared to the other energy components. So it is like in one of your account, you have 1 crore, another account, you have just 1 rupee. So I can say the account with 1 rupee is as good as empty account, right? Can we say this?
Yes.
Yes, sir.
So if you have a motion in which the energy required to perform that motion is negligible, then that motion can also be ignored and can be removed from the concept of degree of freedom, because degree of freedom will take care of only those motion which contribute significantly to the energy value. Now the question is why we are studying all this. The answer is simple. Internal energy of a gaseous system is kinetic energy, but kinetic energy itself is having various forms. So when you know the degree of freedom, you exactly know that how many contributors are present and how much energy this molecule will have, because nature will do something interesting which will come to very soon. So let me quickly define. So what should be the other definition of degree of freedom? So it is the minimum number of parameters in which the total kinetic energy of a molecule can be specified. Okay. So how many parameters you need to know the total kinetic energy of a molecule. So here parameter means translational parameters, rotational parameters, and vibrational parameters. Okay. So we can put the second definition, and what we can say? It is the minimum number of parameters required to completely. So it is the minimum number of parameters required to completely specify the you can see number of parameters which is required to. Okay, let's say called describe the total kinetic energy of any system. So this is the energy perspective, you can say. So we had a motion perspective, now we have the energy perspective. And degree of freedom is a very powerful way to understand the motion actually. So I'll give you context. I mean, not all of you have studied the rotational dynamics, but if you have studied it, I can show you something. In rotation, you all have heard about the pure rolling motion, right? Have you heard?
Yes, sir.
Yes.
If you have heard about the pure rolling motion, so what is pure rolling motion? Tell me, Manasvi, what is pure rolling motion?
Sir, the relative velocity of between like the particle which is in contact with the surface and the surface is 0.
Exactly. So it means no relative motion can be possible between any point of contact, right? So here we have how many point of contact?
1.
1, sir.
So basically it's infinite because it's not a point of contact, it's a line of contact because in a 3-dimensional it's like cylinder, correct? And so it is touching everywhere here. Now this is the ground, isn't it?
Yes.
So we have a line of contact which we generally depict as a 2-dimensional figure with one point of contact. Okay. And this is necessary to know that it's not only one point, it's a points. But anyway, the 2-dimensional perspective is, it is a point of contact, correct? So if it is a, 3-dimensional cylinder, then definitely you will have a line of contact. Let's say it's a ring, and let's think as a point of contact in this case. And because we have only one point of contact, therefore there is no relative motion about this. So this point is called a point at rest. And why I'm saying the point at rest? Because this point, the point exactly below the ground, is at rest, right? Now, if the ground is at rest and you are not moving with respect to ground, so can I say that you are also at rest? Can I
Yeah.
say? And that is why this point at rest becomes a good frame of observation, because when you talk about the velocity of any other point, looking at the velocity of any other point from this point will give you the same answer as you would have got from any other point on the ground, because all points are at rest, right? So all will behave as which frame? Inertial or non-inertial?
Inertial frame, sir.
Inertia.
Because this is at rest, no? The point is at
Yes.
rest. You will later on come to know that the point, this is the only point which is at rest also and having acceleration. Very dangerous concept. So it is a point which is at rest and having acceleration. Is it possible for a point to be at rest and having acceleration? Can you think of other example where the point is at rest but having some acceleration?
Sir, at the highest point when
Yeah,
any
Right.
object is projected.
correct. So
Into
at the
the
highest
air.
point, we know that velocity is 0.
Yes, sir.
So if you throw something vertically upward, then at the highest point, the velocity is 0, but it will be having the acceleration equivalent of the acceleration due to gravity, which is g. Am I right, guys?
Yes, sir.
Yes, sir.
So it is also possible to have a point at rest with non-zero acceleration. So this point is slightly confusing. But anyway, if you think this as a inertial frame, now what I'm trying to say is that whatever velocity you will observe from that point will be same as the answer from the any other point on the ground. Yes or no? You are observing the motion from a point which is at rest. So what you will see? You will see the exact motion, absolute motion. Yes or no?
Yes, sir.
Yes.
Now, to describe the motion of every other point in this body, how many variables we need? Now that's the concept, because the degree of freedom is the minimum number of parameters required to completely describe the motion of body. So how many parameters do we need to explain the motion of the entire body? What do you think?
Sir, every particle inside the body exhibits like two types of motion, like
Mhm.
horizontal and vertical.
No, every point on a body will have same velocity as that of the center mass.
Yes, sir.
And in this frame of center mass, it will have tangential velocity, right?
Yes, sir.
So this particle will have velocity vc because the velocity of center mass is common to all particles. So it is like you can think as a parent or dad. So whatever belongs to father belongs to every kid. Let's say legally. So legally, what belongs to C, the center mass, will belong to everyone, right? So you all are the recipient of what the center mass is having. But in the frame of center mass, every point will perform which motion? Only circular motion, correct?
Yes, sir.
Yes.
So in the frame of center mass, you will have omega into r. If I say there is a omega also. Am I right?
Yes.
So to completely describe the motion of the particle, we need basically 3 variables. Now, luckily in this case, we have 2 variables. One is because center mass is moving in a straight line. So what is the motion of center mass? Is it tightrope, plane, or 3-dimensional box? How the center mass is performing the motion? Is it walking on a tightrope? Can we say?
Yes, sir.
Yes, sir.
How many of you realize this, that center mass will just move straight? And if you all realize that, then you can clearly see that how many translational variable we need to describe the motion.
One.
Only one. And how many omega we need to describe the angular motion? Only one.
One.
The omega, which is clockwise, right?
Yes.
So you need one translational variable, VC, to describe the center mass. And you need one omega to describe everything around center mass. So in total, how many variables you need?
Two.
2. So what is the degree of freedom of this 2-dimensional body?
2.
Two.
Now look at this. If you look at every other point of the body, every point on the body is moving in how many plane? I mean, moving in a plane, or moving in a line, or moving in a 3-dimensional space. Every point. Think of random point other than center mass.
Sir, in a line.
No. every particle except the center mass is moving in which path? Is it moving in a straight line?
In a plane.
In a plane, correct? So to describe the motion of a particle in a plane, how many variables we need?
Two.
We need two variables. So in general, we need two translational degree of freedom. And if you think the rotation of the body as a whole, about how many axes the body is rotating?
One.
One.
So we have only one, rotational degree of freedom. So how many total degree freedom we have?
Two.
You know what is the rule of mathematics? The minimum number of parameters is called degree freedom, and it is the parameter which will also give you the hint or the idea that we need 3 equations to solve this question. You need 3 equations to solve this question. Understood? Just 3 equations. So when you solve the rotational dynamics, you write net force along x equals to mass into acceleration along x for center mass. Net force along y equals to MACY. And net torque about the z axis, because that's the only one rotation, is IZ into alpha. This is how you solve the question of rotational dynamics. And this is inspired from the concept of degree of freedom. So degree of freedom is the direct way to understand that what is the variable requirement to solve any question. But this question can be solved with only 1 degree of freedom. You know which? About this point, you can describe motion of every particle with only one concept, omega, isn't it? Because if you know omega, you can exactly tell the velocity of this particle, right? So about bottom, every point on the body will have a fixed definite motion. So it is like having the knowledge of omega is actually sufficient to completely describe the motion of the entire body. So about the point of contact, the degree of freedom will reduce from 3 to how much?
1.
Only 1. And therefore it is said that to solve any question of pure rolling motion, which is performing pure rolling about a fixed surface should be fixed. There is only one equation. Net torque about the point of contact equals to I about point of contact into alpha. With this equation, you can get the alpha. And once you get the alpha, you can get the everything else. So in 99.99% case, especially if you think about the JEE level of question, every question of pure rolling you can solve by writing only one equation. The net torque about point of contact equals to I about point of contact into alpha. Or if you don't want to use this, you have to use this formula. But what is the difference between these two formulas? While writing the right hand side, this entire thing, this actually becomes net torque about center mass is ICM into alpha. If you want to solve by the 3 degrees of freedom, you need to write the torque question about center mass, not anywhere else. But to solve the question in 1 degree freedom, you have to write about the point of contact. So as a beginner, I always say you start with this method of solving without any ambiguity, because this will lead to the correct answer no matter what. And once you get some expertise, you can switch to this way of solving. So most of the Erudov question or JEE question, you can solve in maximum of 1 line. But it will take some time to realize. Anyway. So let me quickly tell you that what is the real purpose of degree of freedom. So particle will have Vx, Vy, Vz. So what are the possible component of kinetic energy here due to translation only? Can we say half mvx square is one component of energy? Now tell me guys, every gaseous molecule will move in which path? One dimension, two dimension, or three dimension?
3 dimensions.
3.
So how many translational degree of freedom they can have?
3.
3.
What is the probability of having this component, or this component? Same or
Sir, 1 by
equal
3.
or unequal? Yeah, so
Sir,
the
equals.
probability is 1 by 3 for all. Correct? So every event is equiprobable event, yes or no? So let's say a molecule is having, let's say, 3 electron volt energy. Then half mvx square will be how much? If the total translational kinetic energy of molecule, let's say Ke translational of a molecule is 3 electron volt, then what you can talk about or say about the kinetic energy due to the x component?
1 electron.
1 electron volt.
So every component will store how much? 1 electron volt each, right? So later on, this probability becomes our definition called law of equipartition. Equi means equal, partition means distribution. So law of equipartition of energy. So later on, we are going to say the same thing. Now, similarly, if we have a rotation, so a body, now rotation is only meant for the polyatomic atoms, not for monatomic. So you move around X or Y or Z. You may have the moment of inertia Ix. So how many rotational degrees of freedom we can have in terms of energy relation? Half Ix omega x square, half Iy omega y square, and half Iz omega z square. Now vibrational having no formula. So we'll come to vibration later on. And also vibration is not part of JEE. So we'll come to that later on. What is exactly vibration? Now try to understand the shape versus possible degrees of freedom. Okay. So we'll start with monoatomic gas. A monoatomic gas, which is like a dot, is it possible for this dot to rotate? So if you think really as a dimensionless, then should we talk about the rotation for any dimensionless object?
No.
No, because dimensionless means, you don't have a shape definition. You just like a dot. So a particle with no specification of dimension cannot have moment of inertia, or you can say it will have roughly 0 moment of inertia. But for your illustration, I'm putting it bigger. So a monoatomic gas can only translate, yes or no? Because it will have center mass. So however small a particle may be, it will have center mass, and center mass is free to move in all the three directions. So we can say the degree of freedom of monoatomic will be how much? So I can write translational DOF, rotational DOF, vibrational DOF. We'll talk about that also. So tell me guys, for monoatomic gas, how many translational degree of freedom which we can have? Can we say 3?
Yeah.
And there is no question of rotation?
Yeah.
But if it is diatomic, so you can think as a 2-block system. Now every center mass can move freely in any direction. So how many translational it will have?
3.
Now, what about rotation? How many? How many rotation you can think of?
2.
2, sir.
Why not 3?
Sir, because the last one, like when it rotates around the about the axis through which it is connected, it is the same like the monoatomic gas.
Correct. See, I can always draw the suitable axis, and if I draw one of the axis along the length of the molecule, then it seems like every particle lies on the same axis, isn't it? So if we have a 2 particles on this axis, what is the moment of inertia of these 2 molecules about this axis?
0.
So can I say the Ix is tending to 0? So the contribution coming from this term will also be 0. Correct? But the moment of inertia about y-axis is non-zero. Why? Because the first molecule is on the axis, but the second is bond length away. Correct? So the second molecule is away from the first molecule by some distance, d,
Yeah.
and therefore it will have some contribution of energy from half Iy. And similarly about the z-axis, both will contribute something. So about z-axis, the first will make 0, and again second will sorry, second will make some energy contribution. How much? Half Iz. So what you can see clearly that translation is 3 for any molecule. Doesn't matter whether it's a mono, di, tri, tetra, penta, whatever. But rotational depends on shape. So for the linear shape, what is the rotational degree of freedom? Is it 3 or 2? It is only 2, right? Now the question is, what is the maximum number of degree of freedom any molecule can have? Can you think of? What is the worst case scenario?
There are 3 translational and 3 rotational.
And no more vibration.
Sir, vibration will also be there.
So what is the maximum possible degrees of freedom for any molecule? And on what factor it depends? The maximum value.
Sir, the number of vibrational degrees of freedom.
So what is the maximum count, including all 3?
7, sir.
Okay. Okay, tell me who is the most, see, let me tell you what is a constraint. Constraint is very interesting term. The opposite of freedom is constraint. So when you study the laws of motion, you study something called constraint motion, isn't it?
Yes.
So in laws of motion, when you have constraint relation, what does it mean? The motion is dependent. It is not free. So when one block 1 will move, the block 2 will also move in some relationship to the 1, not freely, not independently. Yes or no?
Yes.
So what is the most independent state of any molecule? When none of them are connected to each other, right? So let's say if you have a molecule with n atoms and none of them are connected, let's say all are free to move, then every molecule will have how many degrees of freedom? Sorry, every atom will have how many degrees of freedom? Now imagine they are no longer connected.
Sir, 3 degrees of freedom.
So for n atoms, how many total?
3N.
3N.
3N. So maximum possible is always 3N. Understood? And N is called atomicity. And that is the whole idea. A molecule, okay, is it possible to have more than 3N?
No.
Is it possible to have more than 3N? The answer is no. See, when we have two atoms, imagine there is two H atom. Imagine you have two H atoms. One. Now, tell me how this will move. It can move in all three directions, right? How this can move? So right now, what is the degree of freedom? 3 for this, 3 for this. Am I right?
Yeah.
Now, a constant means when you get connected. So connected means you have some constant now. The moment H2 is formed, the degree of freedom will reduce or increase.
Reduce.
It will reduce. And we know that for diatomic, it has come down to 5 only. Right? So
Yeah.
from the total of 6 for the system, the degree of freedom has reduced to 5. So in any transformation or any reconfiguration of a molecule, so from the free H atom, when you create H2 molecule, you reduce the degree of freedom. You can simply say that you have brought some constraint to their motion. I think we used to play in our childhood something like chain, human chain. So you touch and then there is a chain actually. And then you have to run together as a chain will grow. And then you have to catch everyone, the last one is the winner. Have you played this game in childhood? The chain making game?
Yes, sir.
Yes, sir.
Yes.
Now, what do you call it? This game is called some name, right? Okay, you don't know the name. So I used to call this chain chore. I don't know for what reason, but it's called chain chore. Anyway, so you touch and you get connected. So when you get connected, then can you move freely in any direction? Or your motion becomes restricted?
Restrict.
And because the motion is restricted, your degree of freedom will reduce or increase.
Reduce.
And that is the reason that as more and more atoms come together to form complex molecule, they also suffer huge loss of degrees of freedom. Okay. So that is always there. And degrees of freedom is a very important concept in chemical kinetics, in reaction mechanism, and at various places in chemistry also. In physics, when we study about the motion of, the machineries, gear system. So there also we think of the degrees of freedom. And of course, this is how we design the complex system, that how many degrees of freedom we need to deal with. So the idea is simple. When you have a connection, so when H atom connect together, you reduce in degrees of freedom. You have earlier you had a 3 and 3, 6 as a system, but now as a whole system you have 5. So connection reduces the degrees of freedom. This is what I'm saying. And therefore,
Sir?
Yeah.
Sir, but a molecule is formed only when a connection is made.
yeah, so while making the connection, they reduce the degree of freedom for the system. So every atom had 3. Now the whole atom, the combination will be less than sum of the degree of freedom of all, right?
Yes, sir.
So when n atoms come together, so they bring 3n degrees of freedom, but when they form the connection, their degree of freedom is going to be less than 3n in nature.
Okay, sir.
Now, as you increase the temperature, you increase the degree of freedom or you decrease the degree of freedom. What do you do? you try to make them free from each other, isn't it?
Yes, sir.
So as the temperature of a gaseous system will grow, then the bond may break. You may try to go to the higher degrees of freedom. Okay. So any doubt in this degree of freedom? So what you need to realize that every group of atom, see this 3, this 2, the atomicity here is 2, right? N is how much? So what is the maximum possible degrees of freedom? 6.
Yes, sir.
Out of 6, 3 has for 3 is for the translation, 2 for rotation. How many are left?
1.
So you can say that this particle can have either 0 or 1 vibrational degree of freedom. Now the question is, can we really judge which is the right number for the vibrational? The answer is no. Vibrational degree of freedom is kind of a temperature dependent function. It gets activated to a different level as you give more and more energy. And that is why at a very high temperature, which reaction mechanism is generally considered? In chemistry, you must have heard. High temperature favors or high energy favors which mechanism? Any guess? I hope you all have studied the reaction mechanism in chemistry.
Sir, like KCP, TCP,
What is KCP?
k- kinetically controlled parameter or pressure.
Tell
I
me
think.
some rules in reaction mechanism. So you have some effect, right? Mesomeric effect, isomer, what is
Yeah,
this?
resonance.
Resonating, okay. So there is a mechanism called free radical mechanism. Have you heard this name?
Yes,
Yeah.
sir.
Yes, sir.
Yes, sir.
So when you have the ozonolysis or peroxide, when you use peroxide in reaction,
Yeah.
peroxide also favors the free radical mechanism. So the UV ray coming will be breaking the bond easily. Any high energy intake in any direction will favor the free radical mechanism. So they increase the, at high temperature, you increase the degree of freedom, you break the bond certainly, and then they recombine to go to a newer configuration with more energy release. So high temperature favors the free radical mechanism, and of course this degree of freedom does play a role. And see, every molecule is basically, if you think from the chemistry, from the physics point of view, a molecule is nothing but the cluster of charges with certain configuration. So it will have some potential energy. A new molecule is like a new rearrangement of the charges, and so it's a new energy configuration. Now every moment of charge is not possible, so some moment is more favored than the other moment, and therefore we have certain configuration coming as a major product, and some configuration you also get as a minor product in any chemical reaction. Okay, the purpose is to gain the more stable configuration. So the vibrational degree of freedom having no formula, you can simply say that it can be either minimum 0 or it can go up to maximum value depending on the temperature. So we say that it is generally activated. You activate with temperature. Understood? You activate with temperature. I hope this is clear.
Yes.
Now the
Yes.
third category is, so there is no formula, and because of the lack of formula, we don't study in JEE. Okay. But if they mention, you have to use it. So let's say we have a polyatomic atom. Poly, N is the number. No matter which atomic, atomicity is there, whatever be the atomicity, the translation is going to be always 3. Now rotation we cannot comment unless we don't know the actual shape. So if it is linear molecule, can you give me some example of a linear molecule which is having more than 2 atoms?
CO2.
Carbon dioxide.
Very good. So the shape of the CO2 is linear, right?
Yes.
I think carbon sulfide also, CH2 also. So this
Yes.
linear atom, so linear molecule, you can always draw an axis passing through all the 3 atoms, right? And about this axis, the moment of inertia will be how much?
0.
It means about this axis, we will not get any rotational kinetic energy, isn't it?
Yeah.
So the only significant energy form will be these 2, right? So the rotational difference will reduce to how much? 2. But how many total is possible? 3n. And out of 3n, how many we have already consumed? 5. Correct? So 3n is the total possible, in which 3 is rotational, 2 is 3 is translational, 2 is rotational. So how many we can have at most for the vibrational?
3 and minus 5.
Now the question is, will you have this much or you can have this much? That's the question.
It depends.
So
Yeah, so
we can have.
Yeah, you can. It's not like certainty. You can have, it's like probability. So the vibrational will go from 0 to 3n minus 5. And which value it will attain? It's again very random. It's experimentally, generally it is experimental process. So they do it through some experiment. And vibrational activation means as you increase the temperature of the gaseous system, it will activate some of the component. So I'll show you 1 or 2, activation process. Imagine the CO2 as a 3-block system. You can think CO2 like this. I can move all the 3 particles like this. Or you can move asymmetrically. You can move these 2. You can move all 3 up. You can move 2 up, 1 down. So there are many possibilities, right? You can move the 2 up, 1 down this way also. Okay. So in total, if you count, we have in total 9 possibility. 9 is the maximum number of degree freedom. And out of 9, so I can say for CO2, 3 is here. This is always 2. But a vibrational can be how many? So vibration can be 0 to how much? 3n minus 5. So you can see that for CO2, the answer can be 0 to 4. Now, by default in JEE, you're not supposed to think of vibration unless it is explicitly given in the question that take vibration. So they will tell you some sentence that, okay, assume one vibration degree of freedom. So it means you add only one. Assume two, so add two. Assume three, so add three. Assume maximum, so add maximum, which is 4 in this case. So vibrational is not part of JEE. So by default, we only restrict our thinking to the translational and rotational. When they mention vibration, we take that vibration into picture. It is clear what I'm saying?
Yes.
Yes, sir.
Now, if we have a non-linear polyatomic, let's say N is the atomicity, the degree, the translation is going to be always 3, right? And because it is non-linear, so if you think of H2O in a gaseous phase, if you think H2 in a gaseous phase, what you can think? O, H, H. All right. So this is the shape. Can we confine all the 3 atoms in a one line along single axis?
No.
And because you cannot confine all the 3 on a single axis, then no moment of inertia can be 0. So all the 3 rotation will be intact, all will be significant, and you will get 3 here and 3 here. Then how many are left for the vibration? Do you realize this?
Yes.
Yeah.
So these are the only answers. It's very simple. It's a 5, 5, 3, 5, 6. These are 3 possible answers. Monatomic, it is 3. Di. So di you can take H2, Cl2, O2, N2. Okay, you have monatomic like a noble gases, He, Ne. So those are will have the 3 degrees of freedom. For diatomic, we have 5 degrees of freedom in total. And then for a higher atomicity, we need to know the shape, exact shape. If it is linear, then rotational will be only 2. Okay. And vibrational, unless not mentioned explicitly, we are going to ignore it, because these springs are, you can think as a very tough spring. So they will be set into motion only when the temperature is really high. So only at some high temperature, they are set up into vibration. Or you can say the spring will become soft as the temperature will grow. Okay. So I hope the degree of freedom is clear to all of you.
Yes, sir.
Yes.
So now comes the concept, the most important concept, then we can move really fast. Law of equipartition of equipartition of energy. So this law simply says that the total kinetic energy of any system, also called internal energy. Now we are again defining this in context of the KTG postulate. So the total kinetic energy of any gaseous system, any ideal, I would say mention ideal gaseous system, is equally distributed among all degrees of freedom. So that's very simple. The nature is unbiased. So nature will never think of sharing the energy differently with different components. So once nature will understand that, okay, you have 5 degree freedom, whatever energy it will give to you, it will be equally shared among all the 5 degrees of freedom. Are you getting my point? What I'm saying? Because as per the rule of probability, every event is equiprobable. So why nature will have biasness in giving energy? It will try to give all energy in equal proportion, isn't it? So now the question is in what proportion? So we decide in terms of degrees of freedom. So it's like if someone is molecule is having 5 degrees of freedom, it will get energy in 5 equal parts of partition. Okay. So it is like there is a subsidy scheme by some government, and every child will receive let's say 200 rupees per month for their primary education in a rural village of India. So 200 rupees per kid, per child. Okay. So imagine that a family having 3 kids. So family will get as a whole how much? Government is giving 200 rupees per child. So a family with 3 kids will get how much?
600.
600 rupees.
600, right?
Yes.
A
Yes.
family with three. See, I'm saying that government is giving 200 rupees per child. A family with 3 child will get how much? 600 rupees.
Yeah.
But a family with only 1 child will get.
200 rupees.
So you may think it's still bias. One family is getting more, but the other is getting less. But no, the scheme is as per the child count, not as per the family count, right? So it is not necessary that the family will get the same. Manav, switch off your video.
Yes.
So a family will get how much? As per the number of child. Similarly, a molecule is not entitled to get the same energy. Every molecule will get the energy as per the degree of freedom. Understood? So a molecule with F degree of freedom will get some energy. A molecule with other number will get some other energy. So we'll now try to understand what is the government scheme in case of law equipartition of energy. What is the per degree of freedom energy? And it is very easy to derive. How? We all know the kinetic energy of translation, right? We have derived this already. And the answer was how much? 3/2 kT. Do you remember this? No.
Yes.
Yes.
So kinetic energy per molecule is how much?
3 by
3/2
2
kT.
KT.
So once you forget, then you can derive from the VRMS. This is the kinetic energy per molecule, right? So you can think a molecule as a family. And in this family, how many degrees of freedom live? How many translational degree of freedom you know?
3.
3. So what
Yeah.
is the kinetic energy per degree of freedom? Can we say like this? And
Yes.
the answer is how much?
Yes. Sir. Half
80.
KT.
And that is why half kT is the fundamental energy quanta. So for a energy distribution in a gaseous system, it is like a child will get this much. And so to find the energy of any any system, you just need to count the child. Once you know how to count the child, it's easy for you to write the energy, because this is the answer which is fixed. So it's like a government scheme is given known to you. It's a half kT per child or per degree freedom. Now your duty is to count the total degree freedom or total child count, multiply by this number, you will get the total energy of system. So let's try to derive the energy for n mole of any gas. Okay. So let a molecule having F degrees of freedom, translational plus rotational only. So we are not considering what? Vibrational. So keep in mind that, okay, I'm only considering the translational and rotational. I'm saying that the total is F, because in JEE the vibration is not there. Okay, if they mention explicitly, I'll show the how to change the calculation. So let's say a molecule, a single family having F kids. So how much energy this molecule will have? So kinetic energy of this molecule will be how much? Tell me.
Um,
Hmm?
3 by
F by 2 kT.
Simple.
Yes.
So if one molecule will have this much energy, so what is the kinetic energy of per mole of such molecule? So kinetic energy per mole will be how much?
Into Avogadro number.
Am I right?
yes.
But we know that the moment K and N come together, it becomes R.
R.
So what is the kinetic energy for N mole in general?
N into F by 2 RT.
So it really looks nice. So now we have a generalized formula of kinetic energy, which takes care of all types. So this K is the Ke translation plus Ke rotation. And the sum is how much? A by 2 nRT. So why I'm writing like this? Because we know from ideal gas equation, the nRT we can replace by
PV.
PV. So now you know the general formula for the kinetic energy is A by 2 PV or nRT. Okay.
Yes.
All right. So the total kinetic energy, which takes care of the only translation and rotation, the answer is simple to remember. The kinetic energy of any system in which we have only one kind of molecule, the answer is A by 2 nRT, which you can also write as F by 2 PV. Is this clear, guys? Tell me.
Yes, sir.
Yes, sir.
Now, since we have discussed one thing in the very beginning, that the internal energy of any ideal gaseous system, how we write? Capital U.
Yeah.
And what we discussed that the capital U is nothing but the kinetic energy of system, right?
Yes, sir.
Yes.
Both are same thing, no? Just a way of saying. So can we
Yeah.
say U equals to also A by 2 nRT?
Yes.
So this is the formula for the internal. So now we have derived the internal energy of a system. Okay. Is this clear? So
Yes.
we'll try
Yes.
to we'll try to think of what happens if we have a mixture of gas. So for a mixture of gas, you may have n mole of one kind of molecule with a degree of freedom F1, N2 of N3, okay. So if such gases are kept in a vessel, in a container, what is the total internal energy of system if the gas temperature is maintained at T, which means the system is at thermal equilibrium with temperature T. Once you know the thermal equilibrium temperature, you can actually write the total internal energy. So what will be that value?
Sir, half RT into N1F1 plus N2F2 and
Sigma.
so on.
Yeah, so can we write summation of
Sigma.
Ni Fi?
Yes, sir.
Yes.
So it is very simple that once you know the equilibrium temperature of any gaseous system, or let's say if you have a you have a gaseous system with a different temperature kept in different container, then suddenly you pour all of the gases into one container, or you have a partition in a long tube which is closed from every side. You have partition and you have a mechanism to remove the partition by switching off the partition, then all gas will mix together and eventually they attain the equilibrium temperature, right?
Yeah.
Okay, so How to find the equilibrium temperature when you mix a gas with different temperature in a different compartment? So let's say we have a finding the so we'll come across mixing of gases in this chapter. So this is very easy to solve. If we have a fixed compartment in which the walls cannot move with some partition and all are adiabatic walls. So I'll come to know what is the adiabatic wall. You know what is adiabatic?
Yes.
So wall through which
Energy transfer not allowed.
correct, heat passage is not allowed. So if you have such walls or such gases system, it means I can maintain each gas at different temperature in their compartment, right?
Yeah.
So I have N1 moles at F1 and temperature T1, I have N2 moles and F2 freedom and T2 temperature, and there is a plug. Let's say some sort of plug is there. Once I remove the plug, the gas will mix together, right? And eventually they will attain only one temperature, T, right? Because a single compartment cannot have two temperature. Yes or no? Tell me.
Yes.
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 In any such question where temperature is the final answer which you are supposed to find, you're only supposed to equate the energy because energy is conserved. So we have to follow the conservation of energy. So to solve such system in which boundaries are not moving, and now this is very important to understand. If you look at the system, the boundary of the system is moving, yes or no?
Yeah.
No, it's not moving. No, the boundary is fixed. For the entire system, the total volume is increasing or decreasing or constant.
Constant.
Whenever the total volume is constant, such system you can think as, as a, of course you can say isochoric process and whatever. But the simple thing is in such system, the only change possible is the change of, sorry, there's no change possible. So it will always have the conservation of internal energy. Is this clear? Internal energy changes only in two conditions. If you have some work done, if the boundary has moved somewhere, or someone has supplied the energy externally. So those questions in which either boundary is in motion or you are supplying some energy, we think of, what do we think of? First law of thermodynamics. Okay. See, first law of thermodynamics, you're not supposed to solve, by some formula. It's a very common sense thing. And if you just apply the common sense, you can solve a large variety of questions. So here the boundary is moving, yes or no? The answer is no.
No, sir.
If boundary is not moving, then what will happen? The energy of the system, the left system, the right system, the sum of energy, can we change?
No, sir.
So to find the equilibrium temperature, what is the initial energy of system? Can I say N1 F1 by 2 RT? Or you can simply say what you said, N1 F1 plus N2 F2 into RT by 2. This was the initial answer.
Yeah.
Yeah.
Now finally we have temperature T, so we can say the final energy is how much? N1 F1 plus N2 F2. Oh, sorry, my bad. This is final actually. The initial was how much?
N1 F1
RT1 by 2.
Yeah. So initial was N1 F1 RT1 by 2, right? N2 F2 RT2 by 2. Am I right? And then you're supposed to, just it's the conservation because no energy has lost in the entire process. So we can say using conservation of energy. And see, that's the basis of first law of thermodynamics. It is simply the conservation of energy. Or you can say it's a work energy theorem. Whatever you want to say, you can put into different language or definition. But at the end, it's just energy relation. So using conservation of energy, what we can say, UI equals to UF. And the moment you equate it, you know the answer. The answer is very simple. The final temperature is how much? N1 F1 T1 plus N2 F2 T2 upon N1 F1 N2 F2. Am I right? So once you know the degree of freedom, it's easy to write the final temperature. Yes or no?
Yes.
Yes.
Yes, sir.
So I hope this is clear to all of you.
Yeah.
Okay.
Yes, sir.
There are some questions which will come, which are pretty easy. You can solve like just like this. So let's say if we have a gas chamber and an whenever I'm saying gas chamber, I'm fixing the boundary, which means I'm making a point that there is no change of volume. So work should not be, think about or thought about. Work is not going to happen because the boundary has not moved. Okay, so that's the basic definition. When work is done, when the boundary moves. Okay. So when ice melts, does the boundary move for the ice? Let's say you have ice cube and it melts. So what do you think? The boundary will move? Yes or no?
Yes.
Sir, by boundary, what do you mean?
Yeah.
Boundary means it's the imaginary surface separating the ice with its immediate surrounding.
Sir, that means if the immediate surroundings are also within the boundary, that means energy goes from the surroundings into the ice.
Yeah, energy exchange may be there, but right now we have to only think about whether boundary has moved or not in the melting of ice.
So boundary will deform, but the total volume will remain constant.
Are you sure the volume will remain constant in the melting of ice?
Just
We all know the density of ice is not same as water, right?
Yeah.
So which one is lighter?
ice is like
Ice.
So when ice will melt, it will shrink because you melt and convert it into denser object, right?
yes.
So the volume will shrink or expand. Tell me. It will shrink, na? So melting of ice means it's a shrinking because there is something called anomalous expansion of water, right?
Yeah.
So in the melting process, volume decreases. So whenever there is a numerical value, whenever there is a decrease or increase of volume, we say the boundary has moved. If there is no increase or decrease, we say there is no movement of boundary. Second thing, for boundary, it is necessary that you have system and you have surrounding. Then only boundary is defined. What if there is no surrounding? Imagine there is a gas with a partition, and next to the partition there is an empty space, completely empty space, vacuum. Then if I remove the partition, gas will expand, yes or no?
Yes, sir.
Yes, sir.
But is there any boundary which has moved? Can you think of boundary which has moved? Tell me.
So the boundary has moved.
No. Boundary is only meaningful when there is a system and surrounding, there is a separation. What you are separating? Nothing. Isn't it? Are we really separating something here?
No, sir.
If you are not separating anything, then you're not moving anything. Therefore, such expansion is called free expansion. And in free expansion, there is no concept of work. So work is a boundary phenomena. It means work is only defined when some sort of interactive boundary, although hypothetical, you cannot see it, but some sort of boundary has moved. So an empty vacuum, completely vacuum, is devoid of something. It's nothing actually. It's completely null. So there is no boundary defined between the gas and the vacuum. And therefore, we never define the, it is like you work against someone. There is some sort of opposition. So work is always defined in context of some opposition. If there is no opposition, there is no work. Why will work if there is no one to oppose you? Simply go and expand. So will you pay the bill if all hotels are free in the world?
No.
So although you have money, you go to the hotel, you just enjoy the hotel, come back home, that's it. So your money has changed?
No.
If everything is free in the world? So there is no energy exchange, right, in such process. So there is no work associated, and that's why we do have a definition called free expansion. So free expansion is a process in which a gas expands against nothing. And therefore there is no boundary movement, and therefore there is no concept of work. Okay. So work is something very complex. In some situation, work becomes difficult to understand. So what exactly work? There is always some opposition. There's always some interaction. You interact with some system, other system. So you as a system interact with something else as a system. So you can say you interact with your own surrounding, and then you either compress the surrounding, or you get compressed yourself, or you let the surrounding expand. In any process, wherever there is a movement of boundary as a whole, first of all, to define boundary, we need to have system and surrounding. But if there is no surrounding, there is no boundary, and therefore there is no concept of work. So boundary, we say that work is a boundary phenomena, and some sort of boundary must have moved. Okay, so a melting of ice is a very, very interesting example. In the melting of ice, the boundary has shrink, right? In the melting
Yes.
process.
Yes.
So in the melting process, because the boundary has shrunken, you can say the boundary has moved. So work is being done. Now tell me who has expanded itself, the system or the surrounding? If ice is my system, then my system has shrunken or expanded.
Shrunk.
Now in physics, when the system considered shrinks, we say there is a
Surrounding
negative work done.
expands.
So we say there is a negative work. Because we are engineers, right? I mean, at least going to become engineers in future. And engineers, creates a device or machine which can perform work so that you can take the leverage of that work. So we design machine to do work. I mean, they will do work on us and we are happy. Now, what is the natural tendency of gas? In gas, we know the tendency is to expand. Is it natural to compress?
No, sir.
No,
So that is why like when a gas expands, we are happy. But when a gas will shrink, then we are not happy, because we follow the law of nature. So gas having the natural tendency to expand, and if it is not expanding for some reason, if it is getting compressed, we say there is a negative work done by the system. In chemistry, what you study? You study work done on the system, right? So surrounding is definitely doing work here, because if ice is shrinking, surrounding is expanding, right?
Expanding.
Yes.
Imagine the universe is constant. If ice will shrink, my surrounding will expand.
Expand.
And because surrounding will expand, so we can clearly say there is a work done by the surrounding on the system, or there is a negative work done by the system itself. These all are terminology which we have to be very careful about. In physics, we create system to perform work. We don't do work on the system. We'll try to get the work from the system. Okay, so that's the whole purpose of physicist. In chemistry, what they want to achieve? They want to achieve some chemical reaction. Okay,
Yeah.
in a controlled way, right?
Yes.
Imagine if the gas will react and expand suddenly, violently. It's very dangerous for the scientist. They may die.
Yeah.
So they do work on the system to have a controlled reaction so that they can study. So they use catalysts to slow down the process of reaction so that they can understand the intermediate, you can say, product. They can analyze and they can proceed. And then they also realize that how to change the behavior if you have some intermediate product. Okay. So there, the idea is not to get any work. Okay. So they do work on a system because they have to carry out something. So in chemistry, there is a work done on the system. But in physics, what is here? Work done. What we study here? Work done
By the
system.
By the system.
by the system, because we want the system to do work and we should relax and enjoy. That's it. So you have built a car, airplane or train. So who is working? So these machines are working and we are just enjoying the luxury of these machines, right? Anyway, so there's a question that in which we have yeah.
Sir, I don't understand the concept of boundary with respect to that gas and vacuum example, sir.
So gas and vacuum example. Okay. So let's say we have a partition. In one side of partition, we have a gas. Okay. And other side, we have nothing. So you're not supposed to push anything. So what I do is I simply move this partition from here to here. Or you can say I remove this partition and this partition comes. So there are infinite partition just after one other at a dx distance from each other. I simply remove this partition. Then gas will expand from here to here. Correct?
Yes, sir.
In the process of gas expansion, tell me which boundary we have moved.
Sir,
Which boundary we have moved or expanded?
sir, the initial one that you had removed.
No, boundary of gas. Gas, the container is not the boundary. The gas is, you can think of some imaginary boundary covering the gas. Okay. So when I remove the partition, now to define, first of all, to define the boundary, we need to have something against the boundary. So what we have against this partition, I mean, against this gas. If I remove the partition, gas will push what? Your vacuum?
Sir, yes, sir.
So vacuum is nothing, no? Are you really pushing something?
No, sir.
So are you doing any work?
No, sir.
It is just like, you go to any, let's say, amusement park and entry is free. So how much money you will spend in going into the park?
Zero.
No money.
No money. So work is exchange of energy. So when you do some work, basically you exchange energy. So are you exchanging energy here with someone?
No, sir.
Is there someone to take or give you energy?
No, sir.
So when there is no one to take or give you energy, we call free expansion. But imagine, imagine we have a situation in which we have a piston confining gas in a cylinder. And of course, what I don't show, that's not feasible for me to show. The surrounding beyond this is also system, I mean, gaseous system, the atmosphere, right?
Yes, sir.
So now to move the piston, I need to shrink the, you can say atmosphere, isn't it?
Yes, sir.
Now to compress the atmosphere, I need to perform some work actually.
Yes, sir.
It is like you're deforming the system, someone else's system. So to perform this deformation task, you have to work against the pressure of atmosphere, right?
Yes, sir.
So as this will go, so piston is not moving. It is the gas which is, pressing the piston, and piston in turn pressing the atmosphere. So can we say it is the gas indirectly doing the work of pressing the surrounding? Can we say?
Yes, sir.
So this gas is actually pushing the imaginary boundary of the, you can say atmosphere. Understood?
Yes, sir. Sir, so is it like a misconception saying that boundary is something that separates two different things?
No, it's correct. No? So there are two different things. Now vacuum is not a thing.
It's nothing. Okay,
It's
sir.
nothing, not a thing, right?
Yes, sir.
So when you think about, okay, nothing, there is no boundary, and therefore you're doing nothing actually. So free expansion cannot entail work. Neither it will give you energy, nor you will lose energy. It is just like you simply expand. Now free expansion will have zero work only for ideal gases. In real gas, things will be very dangerous. So imagine if you have a partition and if you let the gas to expand, you know what will happen? Sometimes it is quite possible that the gas will cool down. Yeah, quite possible. Sometimes it is also possible that in a free expansion, gas will, go to high temperature. Now you may be wondering how it is possible that after expansion, gas will become warmer. Is it possible to make the gas warm by expanding freely? So the real gas is quite different, because in real gas we have two types of energy, potential and kinetic. Do you realize this? Potential and kinetic
Yeah.
for real
Yes, sir.
gas. Now temperature depends on which energy, potential, kinetic, or total?
Sir, total energy.
No,
Only kinetic.
only temperature means only kinetic. So potential is not part of temperature. Potential due to the bond formation, right? The interaction.
Yes, sir.
Understood. So what you need to realize that kinetic energy only, it has to do with the, kinetic energy of system. The potential is a separate form of energy. So when you give energy, and let's say when the gas will expand, it is quite possible that during the expansion, the separation will grow. And under attraction, if the separation will grow, what will happen? Potential will increase or decrease?
Increase, sir.
In an attractive system, potential will
Increase.
increase. Okay. So when potential will increase, in order to follow the conservation of energy, the total energy of system is constant. So potential will increase at the expense of what? Loss of kinetic. See, we
Yes,
are
sir.
not providing any energy. We are simply letting it expand through vacuum. So if potential will grow for some reason, then kinetic will decrease for the same reason, because the energy is conserved. And because kinetic will decrease, so the gas will cool down. Sometimes gas may liquefy also. So in fact, it is observed that during the free expansion of real gases, now real, I'm talking about the real gas. In the free expansion of real gas, it is quite possible that the gas may liquefy. Okay. But since we are free from the world of real gas, we are only dealing with the which gas? Ideal gas. And in case of ideal gas, we don't have any other energy except the kinetic energy. And since there is no question of potential, so there is no question of conversion. And that is why a free expansion of ideal gas will never entail the idea of energy exchange in terms of work done. So there is no work possible in case of ideal gas. Is this clear now? Tell me, guys, is this clear?
Yes, sir.
Yes.
So the boundary is a very, very strong concept in physics. Boundary is defined between two things, not one thing and nothing. Okay. And boundary work is a boundary phenomenon. I must have written somewhere in the notes. So work is a boundary phenomenon. So some sort of boundary must have moved. Then only we say there is some work which is performed. So of course, when you solve question in mechanics of class 11th, there you define F dx, F dx. F is always a force. Force means there is always interaction. Do we write nothing dx? Or we write
No,
F
sir.
dx?
F, yes.
F dot dr means F is what? Interaction. Correct? F is the force of interaction. And F comes from where? It always comes through the boundary only. You interact beyond yourself, isn't it? So let's say a block is attached to a spring or a string. What is a spring or a string doing there? It is doing the role of surrounding, because the block is interacting with the thread, the string, or the block is interacting with the spring. So there is a boundary there. Boundary need not to be some sort of hypothetical idea. Boundary means to whom you interact with. Understood what I'm saying? Maybe.
Yes.
Yes, sir.
You all realize what I just said?
Yes.
The boundary. So in mechanics, you see the boundary maybe as a point contact. In mechanics, you may see the boundary as a surface contact. In physics, you also see the boundary as some invisible, you can say, non-contact force also, like gravity, like electrostatic force, magnetic force. So all these are what? All these are invisible boundary. Do you realize this? Invisible surrounding, you can say, and you interact with the surrounding. So whatever is separating this idea and that idea, the idea of system and the idea of surrounding, whatever is separating of whatever shape, that idea is called boundary. Is this clear now?
Yes, sir.
Yes.
Sir,
Yeah.
sir, so like temperature affects the interaction energy, doesn't it, sir?
Temperature affect the kinetic energy. Temperature, I mean, because there is no interaction in ideal gaseous system, so it doesn't affect. But
So
in
in
real
real
gaseous
gas.
system, because we have potential, so there is a possibility of interconversion of one form of energy into other form. And whenever there is a reduction of kinetic energy, you will say the system will cool down, the temperature will change. Understood?
Yes, sir.
So that is the most you can say important concept when you study the calorimetry. So you must have heard about the latent heat, right?
Yes, sir.
Yes, sir.
So when you give some energy to ice, it melts. In the process, the temperature remains constant.
Yes, sir.
So whatever energy you have given has gone to which form of energy? Kinetic or potential or both?
Kinetic.
In the fusion of ice, you supply some energy. That energy gets in which form? Kinetic, potential, or both?
Sir, kinetic, sir.
Come on. Kinetic means then temperature should increase, no? Every melting or fusion process or boiling process is constant temperature process, right?
Yeah. Yes.
It's the isenthalpic
All right. I
process.
mean, yes, sir.
So temperature is not changing, no? Which means whatever you have given is changing the internal configuration. So the potential.
Okay. Yes, sir.
Yeah. Someone was saying something. Tanishi was saying something.
No, sir.
So the idea is simple. The potential is configuration based. And for potential to exist in a system, there should be interaction, the mutual interaction. The kinetic is the energy by virtue of motion, all types of motion. Temperature depends on kinetic part. So potential is not responsible for temperature part. Now, if I am giving energy to a system and system is not changing its temperature, it means we are giving energy which is changing the configuration without affecting the kinetic energy. That's why the temperature is constant. So basically, it is not hidden. It is not now known today that what we used to call latent heat in the past is the energy which requires to change the internal atomic or molecular configuration, or so to say, potential energy of system. Understood what I'm saying?
Yes.
And this is every region is here. When you melt the ice, if you have heard or studied, the latent heat of fusion of ice is how much? It is 80 calorie per gram at 0 degree Celsius, right? So to melt the ice at 0 degree Celsius, how much energy I need to give for 1 gram of ice? 80 calorie.
Yeah. 85.
But to vaporize 1 gram of water at 100 degrees Celsius, how much energy we need to give as a latent heat of vaporization? Now you don't remember. It's 540 calorie. Do you see the huge difference of energy? 80 for melting, but 540 for the vaporization. How to explain
Yeah.
this to stark difference of energy? Can you explain why we need such a
Sir, the
difference?
temperature is already high, like 100
Hmm.
degrees.
Okay, so what is the logic?
But yeah, the what internal will stay same for
So
boiling.
if temperature is very high, then you need less energy, na? Because anyway you are not changing temperature.
Yeah.
Then
Yeah.
anyone who can explain this? Why the latent heat of evaporation is much more than fusion? Think of potential, you'll get the answer. It's very easy. Tell me why this so?
So when the liquid converts to vapor, so vapors are like really far apart.
Correct.
So like
So
potential energy is
conversion,
almost zero.
yeah,
Yeah.
conversion of liquid to vapor is like you have to bring the atoms or molecules very, very far from each other. So you have to work a lot in separating at large value. So this work against this attraction to bring them far apart or to overcome the attraction at all, the amount of work is very high. So you need to supply much more energy to convert. But conversion of ice, which is solid, to liquid, which is, other form, the conversion will only increase the intermolecular spacing by a marginal value. So melting process do not bring the atom or molecules far apart as compared to the gaseous conversion. It has to do with the potential energy. If you know electrostatic, if you know basic concept of attraction and the potential, it's very easy to understand. Temperature is constant in both processes. Why? Because in both processes there is no consumption of kinetic. There is no increment of kinetic. There is no decrement of kinetic. Yes or no?
Yeah.
Understood to everyone? Why 540, why 80?
Yes.
And
Understood.
what exactly
Yes,
is
sir.
latent heat?
Yes, sir.
Now these are the experiment. These are, you can say, theoretical value. When you do experimentally, the actual in the lab, in the melting of ice, what happens? The boundary will shrink, if you remember. So who will do work on the system? The ice on the surrounding or surrounding on the ice?
Surrounding on the ice.
Surround.
Now when the surrounding will expand, it will do work on the ice. So it will also give some energy, right? Yes or no? Work means you
Yeah.
give energy. So who
Yes.
is giving energy to the ice? Surrounding is giving. Now
Yeah.
atmosphere will give energy to the ice. Luckily, the atmosphere is having infinite energy reservoir. So any amount it will give will not affect something. But the interesting thing is, when surrounding is giving energy to melt the ice, then how much energy we need to give from our side? Less than 80 or more than 80 per gram?
A bit less.
A bit less, because a bit will be
Given by atmosphere.
given by the atmosphere itself. So in the melting process, the real or experimental value of latent heat is less than theoretical value. So we do not take care of the surrounding effect in many theoretical questions unless it is not mentioned. Okay. So if it is theoretical question, you need to be careful about the atmospheric work also. If it is numerical question, ignore the atmospheric work. But if they mention the expansion, if they give the density of water, ice, if they give the pressure of atmosphere, it means they want you to also undertake atmospheric work into consideration while solving the numerical. Anyway, so we'll come to this fact later on. Right now, do you realize the surrounding now? Tell me.
Yes, sir.
Okay. So now there's a question. Quickly, we'll come to this. There is a container, and this container contains some gas. And we have H2 here. We supply some heat. Now this temperature is here T. So you can say you heat this container somehow. And upon heating this container, so let's say we have 2 mole of H2 and you heat it, and this temperature is, let's say, 300 Kelvin. Upon heating, the gas temperature goes to 500 Kelvin, and H2 breaks into 2H. So how much energy we must supply to achieve this? To transform from this state to this state, how much energy you must supply? Tell me. Find energy supplied. So tell me, in the both process, have we moved any boundary here?
No.
Should we think about work done here?
No.
And if we are not thinking about the work done, then what we should think about? Internal energy. Okay. So once you think about the internal energy, your job is done. So can you see the change of internal energy? Because whatever energy you give, you will give as per the requirement. Correct?
Yeah.
So what you are supposed to do is calculate the initial internal, final internal, take the difference, that is the amount of energy supplied, right? So it is purely conservation of energy. You are not supposed to think much. Just think of conservation of energy and your answer is done. Eventually, the same thing what we are doing as a common sense will become the first law of thermodynamics. So those who try to solve the first law, if you solve by the common sense, the chances that you will get the answer faster and easier. First law is, there is nothing like a first law. I mean, it's common sense to anyone. So what is the U initial? Tell me. Use the formula. What is the degree of freedom of the H2 molecule?
5.
5.
So we can add 5 by 2 N R T. Always express your answer in terms of R. Don't put the R value in thermodynamics. This is the way to calculate always. So how much is the answer U initial?
1500.
What is U final? Tell me. F is how much?
2000 R.
F is how
Sir,
much?
F is 6 here.
F is?
Sir, 6.
No. What is the
No,
F?
3.
F of the H molecule, H atom?
3.
It's 3.
Mm.
3 by 2. What is the number of moles?
Sir, here it would be 4.
4 more.
Correct. So F by
R
2
is
N R T is how much?
500.
So how much is the answer?
3000.
So how much energy you need to supply?
1500.
So to change the state of the gaseous system from the left to right, the amount of energy required is this much, and you're not supposed to think of even work done. But the reason is simple. The boundary has not moved. So these all are basically your isochoric process. But I'm not using the word isochoric. You know why? Because this is not a process. Now you may be wondering why I'm saying this is not a process. A process is a process is said to be a thermodynamic process if the state is well defined at every instant. Here the state is defined in the beginning. Once you add energy, it will have some chaos. Vigorously, energy will, distribute. The gas will move randomly, and eventually it will settle down. Eventually, after a long time, at some temperature. So once it will settle down at some temperature, so we talk about the equilibrium state. At equilibrium, we can only write the energy. At equilibrium, we can only write the energy. Process we write between two states when it is changing slowly. So that's why it is not necessary that every change is a well-defined. thermodynamic process. It is not required. But energy conservation is like a fundamental law of nature. So whether it is a well-defined process or some random process in which you only know the initial state, final state of equilibrium, and the intermediate states are like it's not in equilibrium. In such case, energy is a way to proceed. You write the answer in the beginning, you write the answer at the end when things have settled. Find the difference, you know how much energy is required. I hope this is clear to all of you.
Yes.
Yes, sir.
The third variety of question they ask is, the third variety is the ratio of energy. So let's say there is a gaseous, you can say, a system. Let's say the total kinetic energy of the system is some value, U naught. So they'll ask you what is the ratio of, or simply what is the value of KE translational and what is the value of KE rotational. So what is the KE? See, the total you know is, if this is given, can you find this and this? Tell me.
Yes, sir.
So how many translation here? Tell me, guys.
Sir, 3/2 nRT.
How many translation?
Sir, 3.
Very
Three.
good. How many rotation?
2.
So the KE trans upon rotation is 3/2, right?
Yeah.
Yes.
Yes, sir.
So this is the ratio of translation and rotation in this case. So how much is translation?
3/5, you know.
And this is
2/5.
understood? Simple.
Yeah.
So once you know the
Yes.
ratio, you can find the each component of energy in a given system. So they may ask you the individual answer also. Okay. So I hope this is clear to all of you.
Yes, sir.
Now we'll go to something interesting. Molar heat capacity. So if you know basic calorimetry, what is heat capacity first of all? Heat capacity is what?
Heat that must be supplied to a given amount of substance to increase its temperature by 1 degree.
Correct. So it is the amount of energy which you must supply to a given substance to increase its temperature by 1 degree Celsius, or more precisely from 14.5 to 15.5 degrees Celsius. Now what is said because of some scientific reason. So they take the range 14.5 to 15.5 because that's the most stable, you can say, a range in which answers is most stable. So for any amount of substance with any temperature which we don't know, if you supply some energy, let's say dq, and by virtue of this energy, let's say the temperature has gone to change by dt. So to change temperature by dt, how much energy we need? To change temperature by dt, how much energy we need? Tell me. dq.
Yes, sir.
Yes.
So to change temperature by 1 degree, how much energy we need?
dq by dt.
dq by dt.
And by definition, this is called heat capacity. So heat capacity is defined as now, heat capacity is a really bad thing. Why? If the amount is small, you may do this at home. Can you find the heat capacity of any ocean, desert, or anything like that?
No, sir.
So what you do in such case, you take the one unit mass of that object and then you find the heat capacity. So when you find the heat capacity of unit amount of something, the name changes. What we call?
Specific heat capacity.
So we call it specific heat capacity. So the word specific means something you are doing the same thing, but for a unit mass. So now the next thing is called specific heat capacity. You can use small c or s. So s is convenient because c may be confusing. So how we define this? So S is defined as heat capacity per unit mass, right? Isn't it?
Yes, sir.
So heat capacity per unit mass is called specific heat capacity. So S we write as 1 by m dq by dt. Correct? So dq we can write as ms dt. It is clear? Tell me, guys.
Yes, sir.
Yes.
Okay. So this is the specific heat capacity. It is about mass relation. Now the problem is in gases, we are not comfortable in terms of mass. So we talk about moles, right? So we thought of defining something new which can get rid of the mass because mole is more meaningful. So here we define molar heat capacity. Symbol is same. So we write as small c only, but in a context you can call it whatever. So this is c, not a very big c. So by definition, the molar heat capacity is what? It is the heat capacity per mole. That's it. Let me get it small. Okay, how to distinguish this? Okay, anyway. So when you define again the same thing, heat capacity for 1 mole of substance, it becomes molar heat capacity, and it is a convenient unit for gases. So in gases, we don't talk about the specific, but for liquid or solids, we talk about the specific. So you cannot C equals to how much? dq by n dt. So dq is how much? nc dt. Understood? It's very simple formula. So for gas, if you know the change of temperature, if you know the molar heat capacity, then you know the amount of energy required. So this is the formula for dq for gas. It is nc dt. Now you must have seen somewhere CV, CP, something like this, right? So CV, CP are the specific thermodynamic process, but C is the generalized process. So C can be for anyone. So as long as you don't know about the process, you have to write NCDT. Once you are sure about the process, you can put its a specific name which is known to you. So this is the next concept we are going to understand. The dq is NCDT. Okay. So now imagine this case. So if we have a piston cylinder arrangement, So this is the piston cylinder arrangement. In thermodynamics, this we call engine. So whenever someone is using the word engine in their life, think of a piston, a cylinder, in which piston can slide freely along its cross section. Okay. So now imagine if somehow I weld this piston to the cylinder. Now it is fixed. Now what will never happen? What will not happen here? The boundary will never move, right?
Yeah.
And always remember that the outside is at atmosphere. So I'm not showing by dotted lines. Okay, you can understand its atmosphere is there. Now by fixing the piston, I make sure that there is no question of work. Okay. So whatever energy you give to this ideal gaseous system, this energy will be changing which part of energy? You are giving some energy to the system, such system. What will happen?
Kinetic energy will increase.
Correct. So can we say the internal energy will grow?
Yeah.
Yes, sir.
And in this case, is it easy to say that the dq must be equal to du here?
Yes.
Yes.
But this is interesting one. Here, the process is happening. The process is happening without change of volume, right?
Yeah.
So in physics, we call this as CV, which is called the molar heat capacity. At constant volume. What does it mean? Keeping the volume of a gaseous system fixed, how much energy I need to increase the temperature of the system by 1 degree Celsius per mole. Correct? So what is the definition of CV? Amount of energy required to increase the temperature of ideal gaseous system by 1 degree Celsius. Okay. Amount of energy required to increase the temperature of ideal gas system by 1 degree Celsius per mole keeping volume of system constant. See, this is not the issue with the liquid and solids. They don't expand as vigorously as the gas. So in gas, the energy requirement will also depend on which process the gas is undergoing thermodynamically. And therefore, process will change the answer. So CV is a kind of process. It is not a in general process. It is one type of process in which you fix the volume. You make sure that volume will never grow. And then you try to calculate that how much energy is required to raise the temperature of 1 mole of gas by 1 degree Celsius. Okay. And when you do so, you define CV. So what should be the definition of CV? Can we say CV equals to dq by n dt? This is the definition of any C. See, whether I write the subscript V or not, the C will have this definition. Am I right?
Yeah.
Yes.
Okay. So I can remove this V. This is the in general definition of C. But if C will go to CV, the dq will go to du, isn't it?
Yes, sir.
Yes.
Because CV means the energy given will definitely change the only internal energy, and that is where the du has got a fixed relation of formula. Du is always n CV dt. Can we say dq is always n CV dt? Is it correct to say?
Not necessary.
This we can add only for
Constant volume.
isochloric process, right?
Yeah.
Yeah.
So if the process is not isochloric, this is not valid, right? But this is always valid. Which one?
dq equal to NCDT.
This is always true. So process driven answer is this, and that's why this answer is always true. Why? Because whenever there is a CV, there is a DU. DQ is equal to DU, right? Now, for any other process, DU remains same. Because you have calculated already a DU from the CV process. So the formula for DU is, I mean, it is going to be same for any other process also. Because as the process will change, the other part will come into picture, the work will be done, but DU will follow the same formula, NCV DT. So the one formula which remains always fixed is NCV DT.
Excuse me,
Okay.
sir.
Yeah.
I did not get this part.
The du you have derived using this concept, right? That keeping the volume constant, the dq is equal to du. But
Yeah.
once you have derived, this is like the formula for the change of potential. Change of potential is always this formula. It is always true.
Okay.
Like no matter if a gas undergoes, let's say some other process, let's say it goes isobaric process.
Yeah.
In isobaric process, the dq will change.
Yes.
dw will change.
Hmm.
But du will follow the same formula.
Okay.
Oh, why it will come? We'll come to this very soon. No. So always remember this formula is going to be the backbone of every calculation of thermodynamics. du equals to NCV dt.
DT.
Understood?
Yes.
And then now let's think of the next process. So the next process is called isobaric process. So we have the similar piston cylinder arrangement. Let's do this. Okay. Now, in this case, now what you can realize that the piston is free to move. Okay. When you give some small amount of energy to this gas, what will happen? The gas will shift towards right.
Yes.
Now, why it will shift towards right? So once you give the energy, the gas will expand. Now, because the piston is free, so it will hit the piston with greater momentum because of the increased temperature, right? But
Yeah.
as a result, it will expand, and the energy which you gave will be consumed in the process of expansion. Why? Because you always remember that whenever you expand, you compress someone. Whom you compress?
The surrounding.
The atmosphere, right?
Yeah.
And because you're compressing the atmosphere, you're giving some energy to the process. In the process of compressing something, we need to spend some energy. Okay.
Yes.
So boundary has moved. So we say in the process of shifting, there is some work performed. So how much energy you gave to the system? dq. Out of dq, how much energy it consumed in doing the work? dw. So what energy it will get as a change of internal energy? Tell me. The difference will be equal to what? As per the conservation.
The change in internal.
Change in internal.
This is the first law of thermodynamics. Anyway, Imagine the pressure as P, and this pressure must be same as the P outside. Why? Because the piston is at rest, so it means the force from this side and this side must be equal.
Same. Yes.
So surrounding, if I say P naught, this is also P naught for the
Yes.
obvious reason. Okay. And let's say you increase the volume by some value. So let's say you move by dx, and the area of cross section we call as A. So what is the force applied by the gas on the piston? Force applied by the gas on the piston is how much?
P naught into A dx.
So work is defined as force into displacement.
Hmm.
Now in
Mhm.
gases system, we never write a force into displacement. We write a dx as change of volume, right?
Yes.
So that's why you see
Not
always
to-
P dv. You don't see F dx because it is more convenient of writing this way, right?
Yes.
So now, if you use the equation 1 and if you substitute the value, what you can write? Look at this carefully. So here we are maintaining the pressure. So the process is called Cp, and Cp we can write as dq by definition. Can we write like this? Tell me guys, yes or no? So
Yes.
Cp is dq by dt. Now here, to raise the temperature by 1 degree, do we need more energy than before, or same energy than before, or less energy than before?
Sir, more energy than before.
Because some part of the energy will be consumed in work. So we need to give more energy so that we can again change the temperature by 1 degree Celsius. So can we say the Cp process will take more energy than Cv process?
Yes, sir.
Yes.
So can we say clearly that Cp is always more than Cv?
Yeah.
And that's logical, no? Because here the dq is, so we can add dq equals to how much? For this particular case, we can add dq equals to n Cp dt. Am I right?
Yes.
So from equation 1 and 2, can we add n Cp dt minus p dv? Let's call p dv. That's p naught is not okay. Then p naught dv. That's fine. Equals to du, and du I have said it is
NCV.
n Cv dt. Equation 3. Now the question is, we have two terms with dt as a differential, but one term is with dv as a differential. So whenever you want to remove the differential in from one form to another form, the thumb rule is use the ideal gas equation. What is that? PV equals to
nRT.
whenever, always remember whenever, because see this P, this V, this T, all are connected with this relation. So to get the differential relation, we always go back to the ideal gas equation and we differentiate both sides. So when you differentiate here, luckily P is constant, but let me show you how to differentiate. So we can add as P dV plus V dP. It's like a product rule. N R we take as constant because it's a closed system. We don't have gas leaving the system. In which case when the gas is leaving the system or coming into the system, the N will change. But so far we have a closed system. We can ignore the change of N. We can write NR as constant. So we can write dt. This is the general way of differentiation. But in our case, which term is 0?
VDP.
VD.
Because the pressure is not changing, right?
Yeah.
So the rule is simple. If you really want to master this thermodynamics, first you have to understand that, okay, how to proceed in every step when you get stuck. So when you have differential with, see here we have too many differential, dt, dv, and yeah, there are two differential. If you want to convert into single differential, always try to use the ideal gas equation, differentiate the equation as per the condition. One of the term will go away and you can substitute to get the answer. So what you get here is P dV we can replace by.
nRT.
NRDT.
So now we have equation 3 and 4. So from 3 and 4, what we can get? So from 3 and 4, we can write what? NCP dt minus PdV. I can write as NRDT. That's fine.
Yeah.
Equals to NCV dt. Correct.
Yes.
And now you can see N dt gets cancelled everywhere. And you get the famous version Cp minus R equals to Cv, which means Cp minus Cv equals to
Constant.
R, right?
Uh,
This is called the Mayer's relation,
Yes.
correct? What do you call Mayer's relation or something else?
Mayer's relation.
Mayer's relation. Yes.
Is this clear?
Yes.
Yes.
So now Cp minus Cv is R. So now, as we know that this ratio, okay, because Cp is more than Cv. Now you must be wondering that how, see, these are a macroscopic treatment of the same thing, right? Now we are treating everything with some bigger terminology. We started with the degrees of freedom, energy per degree of freedom, and so on. And suddenly what we are seeing that there's a big formula, right? NCVDT, NCPDT, and so on. But later on, you will realize that internally everything is connected with the degrees of freedom. And to see those connections, we have to go one step deeper, because Cp is more than Cv. So Cp by Cv is always more than 1. And in thermodynamics, we generally take the ratio as some characteristic. And we call this characteristic as gamma. This gamma is called adiabatic exponent, because of the way you get the formula. So this is called adiabatic exponent. Okay. And we always want to write the answer in terms of adiabatic exponent and capital R. So we know these two formula. Cp minus Cv is R. Okay. Let's call equation A. And let's say the ratio is called gamma. We just call equation B. So tell me how to convert, or write this from these two equations, Cp as well as Cv in terms of gamma. So what we can write Cp? Cp is how much? Gamma Cv.
Gamma CV.
And if you substitute here, what will get? Gamma Cv minus Cv equals to R.
Yeah.
So Cv is how much?
R by gamma minus 1.
Simple. And if you know this Cp will be how much? Gamma times Cv. So Cv, we have got the answer. So can we write like Cp equals to gamma R by gamma minus 1?
Yes.
Why we are writing? We'll come to this. So we are writing to get the next formula. So internally, everything has to do with the degree of freedom. So what we know that Cp we got gamma R upon gamma minus 1, and Cv we got in the examination. If you forgot, that's just use the two definitions, you get the answer. So I don't think it's very difficult, right? Is it difficult to remember?
No.
No.
We know the potential, internal energy formula du equals to NCVDT, right?
Yeah.
This is the change, so we can write as U equals to NCVT. Okay. Because why we are writing like this? Because at absolute zero, we assume the internal energy of system to be 0. That's why if you compare everything with respect to the absolute 0, which means 0 Kelvin, then you can always write du as NCVT and U as NCVT. Okay. Now Cv we just derive. How much? Cv equals to how much? R upon.
Gamma minus
You can see again we have something like nRT.
PV.
So we always have the relation PV upon. Anyway, but this is not the idea. The idea is you wrote earlier the potential, the internal energy in terms of degrees of freedom, right?
Yeah.
And what you got? The earlier you had the answer A by 2 nRT.
Mm.
Now you have the answer. nRT by gamma minus 1.
Yeah.
So if you compare both, what you can say? A
If
by
it's-
2 is same as 1 upon gamma minus 1.
Yeah.
So gamma minus 1 is same as
2 by
2 by f. So gamma is 1 plus 2 by f. Basically, the ratio of CP and CV only depends on the degree of freedom, isn't it?
Yeah.
Yes, sir.
Do you all realize this, what I'm saying?
Yes, sir.
Yes,
So
sir.
degree of freedom is like the internal connection. See, everything has to do with the degree of freedom. Okay, so whatever we have described as per the KTG theory, even the thermodynamics is connected from there only. So now you can clearly see that the ratio is purely configuration of, or you can say ratio is depending only upon the nature of
Degree of freedom.
the degree of freedom. It's just a function of configuration, the shape of the molecule, right?
Yes.
Imagine such a complex world depends on the shape. That's very interesting. So no matter what is the number of moles or whatever, for any process, the CP and CV, the ratio is always this value. Okay. And this is not simple thing. From here, you can actually get some more deeper idea. Okay. So if you want to write, let's say dq for isobaric process. So if someone is writing the NCP dt upon NCV dt, which is in some context, if I say for, this is very interesting, for isobaric process, NCP dt and NCV dt will be how much? 1 plus 2 by f.
Yeah.
Because I'm just multiplying with NDT both sides, right? Numerator and denominator. We also know that this is nothing but the dq.
And you.
So it's so interesting that for any thermodynamic process which undergoes isobaric process, the ratio of heat supplied to the change of internal energy is a constant behavior. It is not going to change. I mean, of course, I'm doing it for the isobaric process. So interesting. If the process is isobaric, I just need to know the degree of freedom. I know this ratio. So if I give you the du, you can find the dq by doing nothing. Just use the formula. Now, the ability to use correct formula in the situation will make the calculation really fast. So if you want to solve some question really fast, you need to see all those connections. Now, as a beginner, it's not easy. I mean, you have to practice a lot to actually get acquainted with all this process of writing. So the formulas are simple, but if you can see more deeper, you will enjoy this process of solving question of thermodynamics really fast, because everything is internally connected, right? So you can also see that dq by du is how much? Gamma. So basically dq is how much? Gamma du. Very interesting, right? So
Yeah.
in the world of isobaric process, this is only for isobaric process, not for any other process. So it's a very exclusive treatment of the relation. So you can always write down the relationship. Let's say if someone is asking that, okay, a system is given 100 joule of energy, and what is system? They'll tell you system is let's say H2 gas. A system, okay, a gas chamber containing 3 mole of hydrogen gas is given 100 joule of energy. Okay, if the gas undergoes isobaric process, tell me the change of internal energy. So what is gamma for the hydrogen gas, H2 gas? Tell me.
5.
1 plus?
Sir, 3 plus 2.
Yeah, so 1 plus 2 by 5,
2 by 5.
Yes, sir.
which is 1 plus
1.4.
7 by 5.
7 5,
1.4.
1.4, right?
Yes.
Yes, sir.
So 1.4 you have to divide. So dq is given 100. So du is going to be how much? 100 upon 1.5. That's it. And you can do it mentally because you know gamma relation. Even if you don't know what is gamma, derive from 1 plus 2 by f, isn't it?
Yeah.
It's very easy,
Yes.
no? No. Is it difficult? Tell me, guys.
No, sir.
So quickly, so gamma is 1 plus 2 by f. What we call this formula? So
It's
we call okay, Reed's formula or Reed's, however you can pronounce. So gamma is 1 plus 2 by f. Let's do it for something simple. For a monatomic, we should remember what is monatomic? 1 plus 2 by?
3.
So the answer is?
5 by 3.
So as f will grow, gamma will decrease. So
Yeah.
gamma is going to be
Yes.
maximum for the monatomic, right?
Yes.
Because with the increase of degree of freedom, the gamma will decrease, right?
Yeah.
So gamma monatomic is 1 plus 2 by 3, 5 by 3, which is roughly 1.67. For diatomic,
fine.
so here the example is H2, O2, N2, or whatever. Generally, you will get question like hydrogen, oxygen, nitrogen, and so on. For diatomic, the famous examples are, sorry, what I'm writing here.
Sir, diatomic is
Yeah,
correct.
this is the diatomic. Okay, just a minute. So for mono, what will get the answer? Helium. Okay.
Neon,
Neon.
argon.
Argon, that's it. I mean, this is the common example. For a di, will get the H2, O2, N2, etc. But you will also get the case of CO2, because for CO2, it's a special case. The vibration is 0. If you take vibration as 0, then the gamma remains same as the diatomic, right? Because
Yeah.
it's linear. So for every linear, the rotational becomes 2, right?
2.
So F will be also 5.
Yes.
So this is a special case you should remember. For triatomic, let's say a vapor, H2O. So if it is non-linear, let's take the case 1 plus 2 by 6. So this is for diamond. This is the diatomic or gamma linear. I mean, it's very bad writing. Linear polyatomic, right? Same as this. And for non-linear, polyatomic, what you can say? 4 by 3. So you can think of H2O. Okay, etc. Now, what is most important is the air. So what about the gamma of air? So air is comprised of what? Roughly 78% nitrogen.
Yeah.
And 21% oxygen. And 1% something else. So we can make it 22 and make it, we can end it like this. So we can take a roughly 78 and 22. Okay, that's 2 major component. So how to find the gamma for the air? So essentially you can see both are diatomic, isn't it?
Yeah.
So gamma of air is same as gamma of diatomic. So answer is 1.4. Is this clear? Now you need to know certain calculation in order to solve question. Finding the molar mass of air. So for a pure element, we know the molar mass. Generally, it's given to you. But what if we have a mixture of gases and then we are supposed to find the molar mass? So molar mass having the formula, it's like a percentage abundance into m of the element summation. That's simple formula. So you need to know in what abundance it is existing in nature, and you multiply it to get the molar mass. And that's why you have seen that sometimes molar mass comes as a fraction. Let's say for chlorine it is 35.5, right? So why the fraction comes in molar mass? Any guess?
Because of
Then
different
isotope.
abundance of isotopes.
Correct. Because of the different abundance of isotope, the value changes. So you write that way. So in case of air, okay, I'll mention here only. In case of air, it's very easy. So you can write 0.78 is the percentage I can convert into fraction, and mass of N2 plus 0.22 into mass of O2. That's it. So mass of air turns out to be how much? 0.78 into N2 is how much? 28. 0.22 into how much?
32.
MO2.
32.
So this will give you the answer 28.88. I think so. Just check. Gram per mole. Isn't it?
Yes, sir.
Yeah. So 28.8 is right answer. And you're supposed to remember this answer for the purpose of examination. The last concept before I leave this class. And on this simple definition of formula, you will get the question. Calculation of gamma mix, CV mix, F mix. So to find the gamma of mixture of gases, CV of mixture of gases, F of mixture of gases, there is simple rule. Conservation of energy. That's it. So you write a U final equals to U initial. Express the answer in terms of gamma, CV, F mix, because now we have the three formula. U we can write as A by 2 nRT, N CVT, right? And the CV we can further write as gamma. Correct? Hello, hello. Am I audible, guys?
Yes, sir.
Yes, sir.
Because I can write U in three formats. So you can write F mix as per this relation. So I can tell you directly the answer will be the two things are easy. F and CV is easy. It's plain forward. So F mix will be summation of Ni Fi by Ni. That's it. CV mix summation of Ni CVI Ni. That's it. Now gamma mix is slightly interesting because gamma is in the denominator. So, but I'll show you how to write it. So for the entire system, so when you say this is a mixture of gas, then you assume the gamma is uniform for all. That's a gamma mix. So how to write the answer? N total, N. Look at this. So total mole N R T by gamma mix minus 1. You are treating the entire mole as one system. But individually, how you would have written the answer? N1 R T by gamma 1 minus 1, right? N2 R T by. Hello, hello. Do you realize this? RT gets cancelled. So the answer is
Yes, sir.
N1 plus N2 plus N3 dot upon gamma mix minus 1 equals to N1 upon this, N2 upon this, and so on. You can use this formula also to get the answer in examination. And based on every formula, there is a one question which is JEE-Mains has asked so far in their life. And if you want to write the answer, you can write it this way also. So gamma mix can also be written as 1 plus 2 by F mix. I hope this is clear, guys.
Yes.
Yes, sir.
Maybe something last. So when you study the sound chapter, the velocity of sound is written as gamma RT by M. So a large variety of question you can solve from here on. A gas with a mixture of molecules, find the velocity of sound. So find the answer like this. So velocity of sound in a mixture of gases, gamma mix RT by M mix, and you're done. So you can solve a large variety of questions from this simple formula and using the relation that we have derived also in the sound chapter. Okay. And the last thing, I wanted to give the last thing. Yeah. So U we can add as NCVT A by 2 RT NRT. So if you compare these two, you can say what is CV? So CV is NT cancel A by 2R. Okay.
Yeah.
This is also you have to write, okay, I have to find the relation. And CP minus CV is R. So CP is how much? CV plus R. So it can write as FR by 2 plus R, which is
1
F
plus F.
plus 2 into R by. Okay. So you can get the CP and CV in terms of this also. All right. In all this calculation, I haven't taken the case when the vibrational degree is taken into consideration. So I haven't taken the vibrational degree, but those who are writing the Maharashtra CET board examination, in their board, the vibrational degree of freedom is also taken into consideration. So for those students who are preparing for the Maharashtra CET and Maharashtra board examination, for you guys, this is the part. Okay. So for CBSE board and other board, everything is covered. So vibrational degree of freedom. So MHCET is special. So rest, those who are preparing for JEE-Mains or CBSE board, you can ignore this part, but nothing wrong in learning this also. So what they assume is they will take the vibrational degree of freedom as F. This F is only for vibration now. Okay. Okay. And what else? So for diatomic gas with F vibrational degree of freedom. Okay. So you need to understand how to write the answer. So the energy, kinetic energy of molecule, how we write per molecule? Per molecule. There is a small change here, which you have to be very careful about. So for diatomic, we know we have 3 translation. So 3 into half kT translational, 2 into half kT rotational, correct? But F into kT vibrational, because one vibrational degree of freedom is equivalent of kT energy. Why? Because in every vibration there are 2 persons involved, not one. So we don't write kT, we write half kT for this guy and half kT for the neighbor oscillating together, and so that total energy of one vibrational degree freedom, we take as kT, we don't take as half kT. So what is the kinetic energy per molecule of diatomic gases? Tell me. What we can write? 5 by 2
5 by
plus F, right?
Yeah.
Okay. So kinetic energy for per mole will be how much? Per mole. So 5 by 2 plus F RT. Correct?
Yes.
Yes.
Okay. And we know that this is the kinetic energy per mole. So kinetic energy will be 5 by 2 plus F in RT. Am I right? Okay. Not okay.
Okay, sir.
And so the
Yes.
the internal energy will be how much? 5 by 2 plus F nRT.
Yeah.
And if you compare this with the formula NCVT, what you can see, what is CV here? Now the CV formula will change, right? 5 by 2 plus F into R. Understood?
Yes. Yeah.
And because CP minus CV is R, so CP will be how much? R plus CV, which
Plus
means 5 by 2 plus F plus 1 into R, correct?
times out. Yeah.
So the answer is how much?
7 by 2 plus
F.
F.
Okay.
Yes.
And I don't have the space left now. Okay. So gamma is how much? CP by CV. The answer will be 7 plus 2F upon 5 plus 2F.
5 plus 2.
So this is the modified formula for the gamma for diatomic. Similarly, you can derive for the triatomic nonlinear. Okay. There is two small concept, but anyway. So now we are very close to the entering the other part of KTG, which is the Maxwell speed distribution. And after the Maxwell, we will go to the first law, which is not very difficult. So I have taught it with laser because now we have got one more lecture. So I wanted to give you more deep insight into the world of KTG. And through KTG, you are supposed to see the world of first law of thermodynamics here itself. Because if you can really see the potential, sorry, I'm what I'm saying. If you can see the internal energy here, once the work will come as an additional feature in the first law, it is very easy to solve question. Also, you will learn in the process, due process, how to bring the new variables, how to solve the differential equation of thermodynamics, how to remove elementaries, and so on. So all those things will be part of the next lecture. The next lecture is very crucial. Don't miss it. You will come to know a variety of, you can say, the insight of the first law of thermodynamics, especially in context of solving numericals. Okay. So theoretically, it is very simple. We all know it's conservation of energy. But when it comes to actually solving the question, then some insight helps us in understanding question with ease and then solving. Okay. So what is interesting here to know? For every vibrational degree freedom, the amount of energy is kT.
KT.
Okay, it's not a half kT, but for translation, it's a half rotation and vibration. So I hope this will be clear to you.
Yes.
If you're writing any examination beyond CBSE, let's say if you're writing maybe VIT or some BITS Pilani, they also ask questions from the vibration degree freedom. Okay. So knowing the vibration is good. JEE may give you vibrational idea through some comprehension, quite possible. So it's good to know because things will change accordingly. So this is the crucial part. Writing the energy relation from scratch. Okay. So all right, guys.
Yes.
Tomorrow you don't have lecture. You have again on Wednesday, right? So on Wednesday you will have again semiconductor.
Sir, tomorrow we have a lecture, right? 6 to 9.
No, that is EMI lecture.
Oh, okay.
So that is not extra lecture. That is regular EMI lecture. So tomorrow evening is your EMI, right?